Good afternoon. I am Shailendra Singh Ojha, Assistant Professor in Department of Electronics and Communication Engineering. Today I am going to discuss amplifier models. If I will talk about amplifiers, then one thing must be clear to all of you that amplifier means the device which can increase signal strength. For example, if you have signal of 0.1 millivolt, if somehow it can be increased, for example, if it can be increased by some device up to, it may be 1 millivolt, it may be 2 millivolt, 10 millivolt, whatever, but the output should be more than input, then this type of device is known as amplifier device. If I will represent any signal, for example, if this is the input signal and this is the output signal, and if it is providing high amplitude and keeping frequency same, then this type of device is known as amplifier device. So simply we can say that amplifier is an electronic device that increases the signal strength. Now, if I would like to classify amplifiers, and especially I am talking about electronic amplifier, then these amplifiers can be categorized into 4 parts, or they can be categorized into 4 parts. From that, one is voltage amplifier, second one is the current amplifier, transconductance amplifier, and trans impedance or trans resistance amplifier. And all type of amplifiers will come in one of these category. If I will talk about voltage amplifier, for example, if I am giving voltage as an input and I am getting voltage as an output, then this type of amplifier will come under the category of voltage amplifier. If I am giving input as a current signal and output also in form of current signal, then this type of device will come under, or this type of device can be modeled by current amplifier. In case of transconductance, if input signal is voltage and output signal is current, then this type of amplifier can be modeled by transconductance amplifier, or transconductance amplifier will be similar to of this device in which be similar to this amplifier in which output will be current and input will be voltage. Similarly, in case of trans impedance or trans resistance, sometimes it is also called as trans resistance amplifier, and in case of trans resistance amplifier, output should be voltage and input will be the current signal, and soon we will see how to represent it with the help of circuit and how to analyze these amplifiers. If we will see here, then this is the voltage amplifier. Actually, this is the circuit or equivalent circuit of voltage amplifier, and we should know that whatever is shown in this shaded portion is the internal structure of amplifier, or it will always, whenever you will draw any equivalent circuit of voltage amplifier, then we need to draw this circuit every time. However, these are the externally connected component. Externally connected component. This is also externally connected voltage source. And for any particular amplifier, Ri will be fixed, AB will be fixed, and R naught will be fixed. So now let us analyze this circuit. How does this circuit will behave, and what is the significance of the various resistors like Ri, Rs, Rl, R naught. So let us talk about these one by one. So see, in every case, we always want that output should be as high as possible. Okay. So if I will concentrate on this circuit, then to get maximum output, actually we are using amplifier to get more output. And so our purpose is to get maximum output from this circuit or any amplifier circuit. So there are certain ways in which we can obtain maximum output. For example, if Vs is fixed, obviously if input will change, if input will increase, then output will also increase. But we are considering, this time we are considering that if input is fixed. This is the internal resistance of this Vs, and this is the input resistance of amplifier. And this is Ri and this is Vi. If Vi will be more, then Av into Vi will also be more. And obviously, output will also be more. So now let us see what will be the condition for maximum Vi. Actually, Vi will be equal to Vs into this resistor Ri upon Ri plus Rs. By voltage divider rule, simply we can write this. So if you will concentrate here, then you will come to know that if Ri will be more, then more voltage will come across Ri and we will have more value of Vi. Or in other words, you can also say that if Rs will be small, then we can get maximum Vi. So both things are equivalent or similar, like Rs should be as small as possible and Ri should be as more as possible. So ideally we can say, practically it should happen that Ri should be much greater than Rs. And ideally we can say that Ri should be infinite, or we can say Rs should be 0. If Ri will be infinite, then whole voltage Vs will come across Ri and we can get maximum Vi, and by this maximum Vi we can get AV Vi will be more and we can get more output voltage. This is what which we can maximize from this input side. Now let us concentrate on this output side also. Once you have maximized the value of Vi, with the help of this Ri, which should be much greater than Rs, then once Vi is fixed, that means AV Vi is fixed. If once this value is fixed, then we will see what should be the condition to get maximum output voltage. Now, let us concentrate on output side. And now you can see here that V naught is equal to what? V naught will be equal to AV into VI multiplied by RL upon RL plus R naught. That means V naught will be maximum if what will happen? When it will be maximum? When RL will be very large and R naught should be very small, or we can say if this will be very small, if this will be 0, then this whole voltage drop, this whole voltage will come across RL. So we can say that R naught should be much less in comparison to RL. So this is for the output side. For input side, we can maximize this if we will have Ri is much greater than Rs. So these are the two conditions which we should remember, or which should be fulfilled to get maximum output voltage. Now, you know here that AV is equal to voltage gain, which is V naught upon Vi. So there are two concepts which we need to remember. One is open circuited voltage gain. Open circuited voltage gain. Open circuited voltage gain means sometimes you used to denote it by AV naught. Open circuited voltage gain is equal to, or how we can find out, when we will open the load resistor. That time this whole voltage will come across this. That means it will be equal to AV naught will be equal to V naught upon Vi. If we will soon we will consider current amplifier also. In case of current amplifier, this parameter is slightly modified, and that time we will call it as short circuited current gain. In that case, in case of short circuited current gain, this load is short circuited. So AV naught is nothing but when we will open circuit this load, that time it is the gain obtained is known as AV naught. And in case of overall voltage gain, we need to consider the effect of R naught RL as well as RS and RI. So obviously open circuited voltage gain will be more in comparison to the gain which will be obtained when RL will be there, and the practical gain, which is AVS, that means the gain which will be obtained when we will consider the signal voltage Vs. It will be equal to V naught upon Vs, and it will be the minimum, because when we will consider this gain, Rs will come into the existence, R naught will come into the existence, and due to this, the actual gain will be slightly less in comparison to the open circuited voltage gain and other voltage gains. This is what which is written over here. So ideally Ri should be infinite, RL should be infinite, R naught should be 0, RL should be 0. Now this is another type of amplifier which is known as current amplifier. So it is very much obvious that in case of current amplifier, current signal should be applied towards input side and current should be obtained toward the output side. One thing. Another thing is this is the internal architecture of current amplifier, or this is the internal circuit of the current amplifier and these are the externally connected components. This is externally connected load and this is also externally connected current source. So now let us analyze this circuit conceptually. The meaning of conceptual analysis is all the amplifiers are designed to obtain the maximum output and let us talk about the conditions which we need to remember to get maximum output, and in this case we can say maximum output current. So when we can get the maximum output current, actually this is Ri, the current which is flowing here is, this is Ri, the current which is flowing here is Ii and this is Ai into Ii. So this current will be maximum when Ri will be minimum, or we can say by current divider rule we can say Ii is equal to Is into Rs upon Ri plus Rs. That means Ri should be as small as possible. Actually current always follow the low resistance path, and in this case if Ri will be very small, Ri will be much less than Rs, then maximum current will flow here and we can get maximum value of Ii and maximum value of Ii which is going to flow towards the load. So practically we can say that Ri should be much less than Rs, or ideally Ri should be 0. Similarly, let us move towards output side. Towards output side, we can clearly see that this is Ii and this current flowing here I naught will be equal to Ai Ii multiplied by R naught upon R naught plus RL. That means RL should be as minimum as possible. R naught should be as high as possible. So we can say that RL should be 0 ideally. And ideally R naught should be infinite so that maximum current of Ii should flow through RL. In this way we can say that this current can provide maximum output. This circuit can provide maximum output. So we should remember these few conditions to get maximum output. This is what which is written over here. And obviously this Ai is equal to I naught upon Ii. Now this is the transconductance amplifier. In case of transconductance amplifier, output will be current and input will be the voltage. And we can always get the optimum values of Ri and RL if we remember this circuit. For example, if we remember this circuit and we remember one thing, that output should be as high as possible. So in this case you can see Vi should be maximum. If Vi will be maximum, then Gm Vi will be maximum. Once you get Gm Vi maximum, then maximum current should flow through this resistor RL. Here Vi will be maximum and Ri will be maximum. So in this case Ri should be infinite. In this case this is current. maximum current will flow if RL will be minimum. That means ideally RL should be 0. Yes, and you can obviously remember that in case of voltage source, its internal resistance is always put in series, and in case of current source, internal resistance is always put in parallel. So, now next is trans impedance amplifier. In case of trans impedance amplifier, output will be the voltage and input will be the current. This is the internal structure. And again you can find out the value of I, Ri, R0 and RL, what should be its ideal value by remembering only one concept, and that concept is derive these conditions for maximum output. In this case, II will be maximum when this Ri will be minimum, that means ideally Ri should be 0. In this case, this is the voltage. RL should be, if RL will be maximum, then maximum voltage can be obtained across resistor RL. So, in this case, we can see that ideally RL should be infinite and Ri should be 0. So, in this way, we can analyze these 4 circuits, 4 equivalent models of amplifier, that is voltage amplifier, current amplifier, trans conductance amplifier and trans impedance amplifier. In next lecture, we will discuss about the low frequency model. Thank you.